We just learned about the sampling distribution of p-hat, the sample proportion. Because p-hat can be understood as a sample mean, assuming that we're working with a variable with values of 1 and 0 only, and as long as the success-failure condition holds, we can model the sampling distribution using the standard normal model. Accordingly, we can conduct a one-sample z-test and calculate z-intervals, just like we did for sample means. So let's examine the sample distribution of p-hat with a sample size of 1,000. Right? So this is a sampling distribution. What we've done is we've taken, just to recall, we've taken many samples, right? Random samples from the population, and each time we take a random sample, we calculate a p-hat, right? And then we make a distribution of those p-hats. So in this case, the distribution is going to be centered on p of 0.33. Right? This is the census from Turin, Italy data. You might ask, though, what is the standard error? What is the standard deviation for this sampling distribution of the sample proportion? Well, since we have the entire population, we can actually calculate the standard error using the following. Right? So the standard error is simply going to be the standard deviation in the population divided by the square root of the sample size, just like before. So since in this particular example, our sample size is 1,000, then we know that the standard error is going to be sigma divided by the square root of n, which is 0.47 divided by the square root of 1,000. So we can do that calculation and we get this value of 0.015. Right? That is the standard error for a proportion. Right? Now the thing is, since we only have two values, 1 and 0, we can actually write out the standard error in a slightly different way. Right? We can use this notation. Sigma equals the square root of p, right, the proportion of successes, times 1 minus p, the proportion of failures. Since we know p equals 0.33, we can calculate it as follows. We take 0.33 times 1 minus 0.33, which is just 0.67. We multiply those two values together and take the square root, we get 0.47. That's the same as before. Right? So when we calculate the standard error for a proportion, we can actually just use that method of just taking p times 1 minus p and taking the square root. And that's the sort of formula that you will see more commonly used. Right? So this is sort of how we typically calculate the standard error for a proportion. Right? You just take p times 1 minus p divided by n, and then you take the square root of that. Right? That's just the same as before. Right? That's just sigma divided by the square root of n. The advantage of this approach, right, is that we can just work with that proportion. Right? So again, typically keep in mind that we don't always know p. Right? That's why we're conducting inferences. P is in the population. So typically we use p-hat as an estimate for p. In a similar way that, as before, we would use the sample standard deviation s as a point estimate for sigma, the population standard deviation. So just to recap, this is typically how we calculate the standard error for a proportion. So let's look at the normal model of the sampling distribution. You can see that the distribution, right, we're using the normal model here. We're assuming the success-failure condition holds. You can see that it's symmetric, it's mound-shaped, and this distribution, this normal model, is centered on p, that population proportion. And then that standard error is given by p times 1 minus p divided by n, and then you take the square root of that. This is just like before, right, in the sense that we write out the standard error in a slightly different way because it's more convenient since we're working with proportions. But the standard error is really just sigma divided by the square root of n. We can also calculate a standard normal model of the sampling distribution. We just recenter our values for these sample proportions. And in this instance, for the standard normal model, the distribution will be centered on 0, and the standard error will be 1, just like before. So with that, you can sort of gain an understanding of the fact that we use the standard normal model, or the normal model, to model the sampling distribution for the sample proportion with a particular standard error. But really, you can see that it's really just like the example with sample means. And with that, you should explore a little bit about what it means to calculate the standard error and what it means to actually use the standard normal model for the sampling distribution for the sample proportion.